This is a lesson for Algebra 2 for section 1-2, and we're talking about properties of real numbers. Our objectives here, and this time through I'm not going to highlight because when I did that, the copy of the completed notes, you couldn't even read the words anymore because it was all covered up. So we want to graph and order real numbers and identify properties of real numbers. So graphing and ordering these numbers is not something that's usually difficult. We're just putting these on a number line. But identify properties of real numbers, that's a little bit back to geometry, trying to remember what properties told us what. And we're going to start off here with the only numbers that you have been experiencing as you've come through your mathematics education so far, and that would be the real numbers. Are there other numbers? Yes, we're going to teach you some more this year, and they're called imaginary numbers. So there are going to be more numbers here. So far you know the real numbers. And people will sometimes have difficulty remembering the names that are associated with the real numbers. And what I do to try to help myself to remember these is to think, okay, real numbers came about because of the need that people had for numbers. So if we start by thinking back in caveman days, a lot of grunting going on. Did they understand what numbers were? Well, eventually what they wanted to do was figure out how many of something they had. So to do that, it would be natural for them to start counting with one, to say, okay, I have one, I have two, I have three. And since that is just natural to start counting with that, those are called the natural numbers, and that's what we use them for. Now, at some point, they had enough of something so that they had to keep track of how many am I giving to this person, how many am I giving to the other person, do they owe me anything? And so they had to have something in their ledger to hold a place when everything was at a balance of zero, when they had everything gone. So instead of those counting numbers or natural numbers, they needed one that had a zero in it. And so those are the whole numbers. And if you say the word whole, you'll notice how your mouth naturally makes that zero. So the whole numbers are going to be the natural numbers, and then we have to add a zero to that. So whole numbers, say the word, and notice that your mouth has that zero in it. Now at some point, somebody needed to borrow something from you and they didn't have anything that they could trade. Maybe they were a farmer and they had a really bad year and so they just didn't have anything, but they're your neighbor and you want to help them out. So you're trying to figure out, how do I write something in my ledger that they're going to owe me for this? Well, that would be the negative numbers. So if we're adding those negative numbers into there, now we have the integers. The integers. Integers are the natural numbers, but they're also their opposites. And then, of course, we have zero in there as well. So integers. Going to work with a lot with integers this year. And then this last group that we see here that we have a blank to fill in, it's not the last group of the real numbers, but it's the last one with a blank, has fractions in it. And you think, all right, if we have fractions, pardon me, and then we have a 1 and a 2, is that considered a fraction? Well, of course it is, because you can write 1 as 1 over 1 and 2 as 2 over 1. If you have 6.1, that's 6 1/10. So that can be written as a fraction. And then you look at that one and you think, is that a fraction? Well, sure it is. That's 222 thousandths, and we could reduce that. So all of these are numbers that could be written as fractions, and our fancy word for fractions in math is ratio. So those are rational, notice ratio right there, rational numbers. Now, last but not least, we see this. Irrational numbers. Well, if rational numbers are numbers that can be written as a fraction, then when you put that IR in front of there, irrational, it means not rational. So in this group, we see in this subset, the square root of 2 and pi. And if we put those into our calculator, we're going to see that they keep going, even though our calculator stops. Our calculator only gives us 10 digits. There's no pattern. They don't stop. They keep going forever. In fact, pi has now been logged to the 10 millionth digit, and there is still no pattern, and it still doesn't stop. So those are the irrational numbers, numbers that we just can't write with a fraction. Now, you may have learned for writing pi as an estimation for it in middle school that you could write that as a fraction. But no, it's not represented exactly by a fraction. So that's going to make it an irrational number. Rational numbers, those are the numbers that you can write as a quotient, and quotient is our fancy name in math for fractions. So we've got quotient, we have ratio. There are a lot of different ways that we could talk about this, but quotient definitely means division. And division, of course, involves using fractions. So we can write these as A over B, which would be our rational numbers. In this little blank, we want to put that it includes terminating decimals, and we have an example there of 1/8, which is 0.125. Now it stops there. It has 3 decimal places, and it is done. We can write that as a fraction because that's 125 thousandths. And if we reduce 125 thousandths, we get 1/8. So terminating decimals are definitely rational numbers. It does include repeating decimals. And you'll remember that this line over the 3 means that the 3 keeps going and keeps going and keeps going like the Energizer Bunny here. So that would be 1/3, and we've seen that before, that basic pattern of 1/3 as 0.3 repeating. So those 3 dots are to indicate this is going to go on forever. Irrational numbers. Well, as I was talking about with pi before, and that square root of 2, we can't write it as a fraction. They cannot be written as a fraction. Irrational numbers do have decimal representations. Those are approximates that we could use, but we're interested in exact answers in math. So we may have to use 1.414213 if we're trying to find a spot for the square root of 2 on a number line, but we know that the square root of 2 goes on forever. So have decimal representations that neither terminate nor repeat. And I want to give you enough time to get all of those blanks filled in there for what you need. So rational numbers, basically root word of rational, ratio. Think fraction. Can I write this as a fraction? Irrational numbers, we cannot write those as a quotient, as a fraction. So no fraction for that one. Now, down here, it says which set of numbers best describes each situation. So what we want to do is read through this and say, okay, if we have to pick some numbers here, what subset of numbers should we pick? And we're supposed to choose from the following number sets: natural numbers, integers, rational numbers, and irrational numbers. So A says the number of people participating in a race. So if you think about that for a minute, you think, okay, if I'm going to figure out how many people are participating in the race, I'm going to count. I'm going to say 1, 2, 3, 4 and count them. And those are the numbers that it is just natural to start counting with. So that would be the natural numbers. B says the time it takes to drive to school. So at first you might think natural numbers, but then you remember, hey, wait a minute. I can drive for a half an hour. I can drive for a quarter of an hour. That means I'm going to have some fractions going on here. So these would be the rational numbers. Now we wouldn't have to be, because this just asked us of the number sets: natural numbers, integers, rational numbers, and irrational numbers, which would we have? So that's a correct answer. But really, we want to think this would just be the positive rational numbers, because we are talking about the time it's taking to do something. Then C says the amount of money in your bank account. Well, the amount of money in your bank account. All right, well, it is $1, $2, $3, but can I have a portion of $1? And you realize, of course you can. You know, that's when you're talking about how many cents you have. So these would, again, be something that we could write as rational numbers. And the amount of money in your bank account, you think, well, should I put positive in front of that? Oh, no, might not be positive. You might go over. You know, they do have some programs now at the bank where you can sign up to, really, they just loan you the money when you go underneath your balance, and that's called overdraft protection. But you definitely can go into the negatives. On the next page, we are going to graph on a number line. This says, what is the graph of the numbers -5/2, the square root of 2, and 2.6, where the 6 is repeating? So -5/2, you might remember as -2.5. If you need to, you can punch it into your calculator to see that. So what that means is we're going to need to go halfway between -2 and -3, and we're going to make a little dot right there, a little point. But what we don't do is label that -2.5. We label it what they wanted us to graph. So up above, we'll put our -5/2. The square root of 2. Again, we're going to use a calculator to figure out where to approximate that. And in fact, instead of doing equals bars, I'll put the little squiggly equals, which means approximates. So it's about 1.4. We need to go between the 1 and the 2, but we need to go a little bit closer to the 1, so not quite halfway. Again, we don't label that 1.4. The label they wanted us to use is the square root of 2. And then 2.6 repeating, well, that's going to be between 2 and 3, but closer to the 3, so about there. And again, I use the label that they gave me. 2.6 repeating. So that's what we need to do. So I'm going to have you go ahead and pause the video and graph what we have for B. Starting this back up, what we would want to do is punch in the square root of 3 into our calculator and see that that's about 1.7. So between the 1 and the 2, a little bit closer to the 2, but definitely give it the label, the square root of 3. 1.4 repeating, well, that's going to be between the 1 and the 2 again, but closer this time to the 1. And my green dot should probably go a little bit further over. And then I can fit my 1.4 in there. And I color-coded mine, so it would be very easy for somebody to grade my answers here and say, oh, well, the green one was the square root of 3 and the blue one was the 1.4. And then I need 1/3. Well, that's between 0 and 1, but it has to be closer to the 0. And I might go ahead and label that one down here because things are getting kind of clogged up there on the top of the number line. But again, notice that it's color-coded so that anybody that graded my paper could see exactly what it was that I intended when I put these numbers on. Down below, problem 3 says, how do the square root of 17 and 3.8, how do they compare? And that means they want us to talk about, are they greater than or less than? Now this first symbol right here, this is greater than. And the second symbol here is less than. And hopefully you remember the alligator saying from when you were in elementary school, where the alligator is always greedy. And so its mouth always points to the bigger of the two numbers. So if this is less than, we know it is because here's where the alligator is going to eat. That's the bigger number. So this would be the smaller number. And you think about what this symbol means, and you'd say to yourself, if something smaller is on the left, its smaller is less than bigger. So we're going to need the square root of 17. We're going to have to figure out what that is. So you'll use your calculator to find out that the square root of 17 is about 4.12, etc. And then we have 3.8. Well, 4.12 is definitely bigger than 3.8, but we have to use the original number that they gave us, that exact number, the square root of 17. We don't use the 4.12. We use that to think, but we don't write that down. Now, would there be another way to write this? Well, of course there would. If we had written the 3.8 down first, we could say 3.8 is less than the square root of 17. So for each of these, we really would be able to write 2 inequalities. We can get those on there. So I'll scoot this up, and I want you to go ahead and write down your answers for B. Again, you can pause the video if you need to. All right, square root of 26 is approximately 5.1. And then we have that 6.25 up there. Well, that means that the square root of 26 at approximately 5.1 is less than 6.25. But we, of course, could write that as 6.25 is greater than the square root of 26. And we would have that one done. So hopefully both of those went very easily for you as you worked through this. Now, getting off of the number line topic and going back to remembering the reasons why we can do the things that we do with numbers. So up here we have the opposite, or it's called the additive inverse. Now to me that name makes perfect sense because additive means, well, we're going to add it to something. Inverse means to undo it. So if I have a 3 and I have to add something to it that's going to undo it, I'm going to have to use a negative 3. So the opposite or additive inverse of any number A is negative A. The sum of a number and its opposite will always be 0. And that addition that takes place there to get us the 0 is called the additive identity. So these situations that you see right here, those are examples of that additive identity. 12 plus a negative 12 is 0, and negative 7 plus 7 is 0. Obviously, these are not the only examples of this. We have an infinite amount of examples, but those would be the additive identity. So for addition, the identity is going to be 0. The reciprocal or multiplicative inverse. I always like that word, those two words, multiplicative inverse. It just kind of rolls off your tongue. So reciprocal is the multiplicative inverse. Now it's a little bit different to think of the multiplicative inverse because it's talking about multiplication and undoing something. So to undo something by multiplying, what we have to do is be able to multiply them together and get a 1. So the reciprocal or multiplicative inverse of any non-zero number A is 1 over A. The product of a number and its reciprocal will always be 1. So product means multiply. So when we multiply a number and its reciprocal together, we will always get 1. So the multiplicative identity is what we see here in these two examples. 8 times its reciprocal of 1/8 will give you 1. Negative 5 times its reciprocal of negative 1/5 will give you 1. So we will have to recognize the properties of real numbers for the Chapter 1 test. So we take a look at this and we see that it's saying A plus B is a real number and A times B is a real number. And up here it says let A, B, and C represent real numbers, and we think, okay, so if you add two real numbers together, you get a real number. If you multiply two real numbers together, you get a real number. What's that called? This actually wasn't in your geometry book. This is called closure. Because what they're doing is they're saying if you are in the real number system and you add two real numbers together, that system is closed. It's going to stay in the real number system. And A times B, real number times a real number, will also stay inside that real number system. That system is closed. Now we look at the second example that we have here, that A plus B equals B plus A, and we realize all they did was switch those two around. And A times B equals B times A, and that's the commutative property, and that one always makes sense to me because the root word of commutative is to commute. And when you commute, you should be thinking about, okay, my parents commute to the cities. They go from home to the cities and cities to home. Look at what's happening here. Home to the cities, cities to home. Home to the cities, cities to home. So when we're commuting, all we're doing is reversing that order, and we know that that's going to work. In the next example, we see the parentheses have moved. Well, parentheses. Okay, what do parentheses do? Parentheses are grouping symbols. Grouping symbols. Well, in real life, if people are grouped together, hanging out together, they are associating with each other. So this is the associative property. It's saying which numbers are going to hang out together. They associate with each other. Now, the next two that we see here, we actually talked about in the examples up above, and we said, all right, we've got 0 plus a is a, and 0 plus a is a. They mentioned earlier that that's going to be the additive identity. Well, yes, because if you add 0 to a number, you just get that number back. You have not changed its identity. Its identity is who it is. So adding 0 is going to be your additive identity. And then multiplying. You think, well, what do I multiply by that I won't change the number's identity? I won't change what it is. And that's going to be multiplying by 1. So the additive identity is 0, but the multiplicative identity is 1. Now we look at the next set and it says a plus negative a is 0, and we think, well, we talked about that one up there too. A times 1 over a is 1. Well, that was up there too. Those are inverses. That's how you undo those numbers. You use their inverses. So a plus negative a gives you 0, and a times its reciprocal, 1 over a, will give you 1. And then the last one down here, this is one we use tons in exponential algebra. And notice how the a has been distributed through the parentheses. That's the distributive property. Now, notice with that one, we don't say it's the distributive property of addition or the distributive property of multiplication, and that's because both of those two things are taking place in this problem. We have addition and we have multiplication. But the column headings here will tell us these are all properties of addition, and these are all properties of multiplication. And so if we say the commutative property, we really should stop and say, okay, but are we adding or are we multiplying? Is it the commutative property of addition or is it the commutative property of multiplication? And use that as an answer. We have some practice down here. Problem 4 says, which property does the equation negative 2/3 times negative 3/2 equal 1 illustrate? So I'm thinking through this and I'm saying to myself, okay, this is multiplication. Now I need to go and look up the property that says if you multiply something and it's reciprocal together, you get 1. So you think, okay, well, let me go back up here if you've forgotten your geometry from last year. And it doesn't take too long for you to figure out which one we're talking about here, because this is definitely the inverse property of multiplication right here. So inverse property of multiplication. Okay, so what if we don't get that chart? You know, how do we think our way through this? Well, as you look at that, you think, okay, negative 2/3. They're multiplying it by negative 3/2, and now it's something different. So it can't be the identity because it didn't stay the same. But what they did was they undid negative 2/3. And to undo something and get a totally different number, that's the inverse. So the inverse property of multiplication. B says, which property does the equation 3 times 4 in parentheses times 5 equal 4 times 3 times 5? And it's not the parentheses that moved. These parentheses are in the exact same places. What switched positions were the 3 and the 4. And that's home to work and work to home. That's commuting. This is the commutative property of multiplication. So reversing that order, that's commuting. And then I want you to give C a try. You can go ahead and stop the video if you'd like. See what you can do with that one. Hopefully you recognize this one right away and said, well, look what they did. They multiplied those together. Now, what's that called when you take a number outside the parentheses and you multiply it by the stuff that's in the parentheses? And that is the distributive property. And remember, this is the one that we don't write whether or not it's addition or multiplication. It's because there's two things taking place here. There is addition and there is multiplication. So that's going to be our distributive property. Now, this one normally in class, I would have you work with somebody else on this, but what I'm going to have you do, because we're doing these as videos, is just go ahead and see if you can figure out what the properties are here. Go ahead and pause the video and try A through F and see how you do. Hopefully you noticed in A, well, it's X, Y, Z, and now those have switched positions. That's your work to home and home to work. So this is the commutative property of multiplication. You take a look at B, and it was F and G that were in the parentheses, but now the parentheses have changed locations. They were here, and now they're here. So it's not the variables that have switched positions, it's the parentheses. Okay, parentheses, those are the symbols that tell me when numbers are grouping together. That's who they're hanging out with. That's the associative property of multiplication. It's which ones are they associating with. Now in C, this isn't the associative property, and that's because the parentheses are still in these positions. What's changed is inside the parentheses. So they reverse the order. Again, that's going to be home to work, work to home. So that's the commutative property of addition, because those were inside the parentheses and there was addition taking place there. That's the commutative property of addition. For D, we have 5 times 1 equals 5. So you took 5, you multiplied it by a number that did not change who it was. That's its identity. So 1 is that identity property of multiplication, or you could say multiplicative identity, either way. In E, 8 plus negative 8 equals 0. They had an 8, they undid the 8 with a negative 8. Well, that undoing is the inverse property of addition, or additive inverse. In F, they added a 0, and it turned out that 0 didn't do anything. Notice how the 0 is here, but it's not over here. And you think, well, what happened then? Well, it didn't change the answer. On the left-hand side, V plus 0 plus W, the 0 didn't add anything to it. And that's because it is the identity property of addition. It did not change what the numbers were because we were just adding 0. So either additive identity or identity property of addition. That's all we have in this section, section 1-2. So this is the assignment. And again, you'll need to write down that this is for section 1-2. And you're going to go to page 15 and do numbers 11 to 33, just the odd, but then you're going to do 35 to 64, all of them, and 66. So whenever we don't write even or odd behind something, that's because we want you to do all of that group. So don't forget to put your name on it, and this will be the lesson for the 7th, which is a Wednesday.